Hi guys, in this tutorial we're going to look at current, charge, voltage and power. At the end of the tutorial you should be able to handle questions like this where you have a current given as a function of time, so you're dealing with AC current, and also know how to handle expressions of voltage given like this. So this is one of the questions you should be able to work out at the end of the tutorial. We're going to look at it as one of the examples. After that, we're also going to look at a question like this, which came in the same paper as the previous one. So we're going to see exactly how we sketch a graph or how we sketch a problem like this. Now let's start by just describing what you need here. Well, when it comes to charge, the first thing that you need here is the symbol for charge. Of course, we use Q. Sometimes it will be small letter q, don't get confused by that. And then in terms of the unit for charge, so charge is measured in coulombs. Now, with that out of the way, it's important for us to understand how charge works, because charge is what leads to current. Current is a concept that we describe a lot in electricity in this course. So because of that, it's important to understand where it comes from. So for us to get current, we have to talk about how charge flows in a circuit. So if you looked at the rate of flow of charge with respect to time, then this is what brings about current. But if this rate is actually constant, if there's no change in the flow of charge, then this becomes equal to 0. In this case, then the current that is flowing is considered to be a DC current, a direct current, where there is no change in the flow. So in this case, of course, generally, the rate of change of current, of charge with time, this is what we're considering as current. Here, of course, we're going to use small letter I to mean AC current, alternating current, current that changes with time. And we're going to use capital I to mean DC current, current that does not change with time. Okay, now, how does it work? Well, this is one expression that we're going to encounter a lot in this case. So this works in an event where you're given current as a function of time. So in this case, of course, we can relate it to the change of charge with time. So if, let's say, they wanted us to find the charge that was flowing given an expression of current, we can easily make dq the subject of the formula, and we end up with current, a function of time, multiplying dt. So notice that here I've just made dq the subject of the formula. And if you integrate both sides, you end up with q being equal to the integral of I, function of time, being integrated with respect to t. So this is an expression that we can take advantage of. So you don't have to memorize this expression. All you have to remember is this definition of current here, to say current is just a change of charge with time. Now look at the first part of this question. In the first part for this question, look at what they're asking us. They're telling us to say, first they say, determine the charge delivered to the device between t is equals to 0 to t is equals to 2 seconds. And then we're given an expression of time, so of current, I mean. So current is given to us as, to say, it will be given by this function, 6 exponent neg 2t. So this function is what actually defines current in this case. So, and then we're being told to say, we're dealing with this from t is equals to 0 to t is equals to 2 seconds. So with this in mind, let's see how we can use that expression to actually work out a question like this. Well, we've just seen that from the definition of what current is, we have dq over dt. And if you make dq the subject, you end up with dq equals to it dt. And integrating both sides, you end up with this expression. So given this, notice that to find q, all we have to do, since the first part is asking us for q, all we have to do is to substitute. In this case, I is 6e to the minus 2t and then dt. So our limits here, we're changing, time is changing from 0 to t to 2 seconds, I mean. So we're changing from 0 to 2 seconds. So how do we continue this? So in this case, let's see. First, we have to integrate, of course. 6 is a constant, so it comes out. We're from 0 going to 2. And then we're integrating the exponent of negative 2t with respect to t. So the integral of an exponent, it's the derivative of the power, which is negative 2 in this case. So we're going to have 6 the derivative of the power, we'll divide it here, -2, and then we'll bring back the function exactly the way it is, and the limit from 0 to 2. So then the next thing here, we can simplify this. So of course, we know how it goes when we use the limit. So we're going to just substitute this, the upper limit, then minus when you substitute the lower limit. So this becomes 6. Let's substitute the upper limit. We can actually bring out that half. The half can come out. So if we bring out the half, this becomes -6/2. And then now, when we substitute the upper limit, this becomes e to the power -2, multiplying 2. And then when we substitute the lower limit, we get, so this has to be minus when you substitute in the lower limit. And then this is now e to the power -2 times 0. So here we have 0 when I substitute the lower limit. Okay, so from here we can simplify. 2 into 6 goes 3 times, so we have -3 here. And then this becomes e to the power -4. Then minus e to the power, the product there is just going to be a 0. So e to the power 0 will just be 1. We can leave it like this, up to us, or we can say -3e -4 plus 3. So this is okay. We'll just write it as 3 minus 3 e to the -4. So this becomes the charge that will flow in that time or in that period. So I hope you're able to see how we take advantage of the definition of current to easily determine the amount of charge that was flowing in the given amount of time. Now the next thing that we want to look at is voltage. Well, when it comes to voltage, the idea is simple. The symbol for voltage is capital V, and then apart from that, the definition of voltage is just the amount of energy that is required to move an amount of charge. Now, in this case, the formula here becomes the amount of energy or the work done in moving an amount of charge. So you have dW over dQ. So this becomes the definition of what voltage is. So work done over charge. Now, if you looked at power in this case ends up, of course, we're going to use the original definition of what power is. So power is just work done over time. So we're still going to look at the amount of work done with respect to time. So this is what power is. But if you recall from elementary physics, you should be able to remember that power can also be calculated by voltage times current. Well, this expression actually comes from a definition like this, because if we used chain rule here, we can easily see that we can write this as the amount of work done with respect to the amount of work done in moving a charge multiplying the charge divided by time. So if you look at this part, this is just our definition of voltage. And if you look at this part, this is our definition of current, charge over time. So perhaps I should use small letter I here to mean this is a current that is changing with time. But of course, it doesn't really matter here. So with this in mind, look at the second part of the question. Of course, the unit for power is just the watt. The unit for voltage is just the volt. So look at the second question in this case. In the second question, now they're telling us to say, find the power absorbed. So how do you find the power that was being absorbed during that time? Well, we have just seen that power is equal to voltage times current. Well, we know what the voltage is. The question does give us the expression for voltage. And if we look at the question, the expression for voltage is here. So you have voltage, a function of time, is equal to 10 di t over dt, and then this is in volts. So if we get this, take it down. So the voltage here is given as, so we have this expression here. So we have this expression for voltage. And if we were to take down the expression for current we have IT, and then what we had was 6e to the -2t, and then this was in milliamps. Perhaps we should take advantage of the units here. And I just remembered we didn't actually include the units here for charge. Well, we know charge comes in coulombs, but what units are we going to have here? Well, if you look at what we used in terms of current, the expression for current was given in milliamps. So when we were getting the charge, for charge you had dq, we had q, you can say we had dq, and then this dq was equal to the current function of time multiplying dt. So if you look at the current came with milliamps. So whatever the case, written in amps, this is just going to be 10 to the power minus 3, the milli part, amps, and then whatever came with the time, which is just t. So in the end, what I'm trying to say here is that whatever the units of charge, they're going to be coulombs, but the 10 to the power minus 3 will still exist there. So this should be millicoulombs. So the final answer that we got here, we had this expression. The unit it's going to have is going to be the millicoulombs because we used current in milliamps. So in this case, let's move on to look at what we have to do now in terms of the power that was being used up. So in terms of power, we remember to say power is just voltage times current. But the voltage, observe this part here. When it comes to voltage, notice that the expression for voltage is given to say it contains the derivative of current. So be very careful in terms of interpretation of this IT here. This is the derivative of current with respect to time. So from that in mind, let's just focus on that derivative for now. The current with respect to time. The current, remember, the current is E, that's 6E to the power minus 2t. So if we're to make the derivative here, so of course, differentiate the power, that's just minus 2, then multiply the power down. So this becomes minus 12. And then apart from this, we're going to have the function, the exponent itself, at 2t. So this is the derivative. So when it comes to the expression for voltage, we can now rewrite it. And this becomes, so remember, we had a 10 first, then the derivative. So we're going to have 10 here, then the derivative, which is minus 12 e to the minus 2t. So this is the derivative. And this was, if we look at the units again, this is in volts. So this is what we have as our voltage. But when we're differentiating, remember, we're differentiating an expression which was in milliamps. So this, in the end, since this is coming in millivolts, in milliamps, in the end, this comes to be in millivolts because this is coming with a milli part, or with that 10 to the power minus 3. So the 10 to the power minus 3 will make this a milli as well. Okay, so I hope you're able to get that. So the next part is, how do we take advantage of this? Well, we go back to the expression of power. Power, voltage times current. So for voltage, we have 10. Of course, we'll multiply the 10 with the 12 there. So you get minus 120 e to the power minus 2t. So this is all just voltage. And then from current, remember, current was 6 e to the power minus 2t. So of course, the 6 and the 120 will multiply. And once we multiply here, we're going to get negative 720 and then e. Now, when you look at this, the exponent, this is exponent negative 2. This is also exponent negative 2. All in all, I'm seeing an exponent, same base. So just add the powers. We end up with minus 2t minus 2t, which is minus 4t. So this becomes the expression of the power. Notice that this expression is also a function of time. So let's hold on to this. We'll come back to it again. Now, let's say we wanted to find the power in a specific amount of time. Like, for example, this question here is just saying, determine the power, find the power absorbed. So if we were to say that they wanted us to find the power absorbed during this time, then we're saying the power there, since we have a specific amount of time, then we can say the power absorbed will end up being the power absorbed at exactly 2 seconds. So this is at t is equals to 2 seconds. Now, of course, let's first look at the units here. How will the units turn out to be? Well, it's all about what we were mixing. In the first part, we had voltage, and we saw to say the voltage was coming with the millivolts. Then this was being multiplied with the other part, we had current, and current was coming with the milliamps. So if you were to just quickly convert this, this is 10 to the power negative 3 volts, and then multiplying 10 to the power minus 3 amps. So if we just now look at this, this is 10 to the power negative 3, 10 to the power negative 3, same base. So you can add the powers. This becomes 10 to the power minus 6, then volts and the amps. So all I'm looking at is this part. We know to say when we multiply this, we get power. and power comes with the watts. The 10 to the power minus 6, we know this is just a micro. So this becomes the microwatt. So this becomes the unit that this expression is going to have here, microwatts. So with that figured out, let's quickly now determine what the power will be at 2 seconds or in 2 seconds. So we've seen that the power is just equal to negative 720, and then the exponent of, we had e to the power minus 4, so that is e to the power minus 4t. But this, since we are saying that we are looking for the power at 2 seconds, so t is equals to 2 seconds, then this becomes minus 720 e to the power minus 8 when you substitute t there, 2 seconds there. So this becomes the power. And the units, of course, this is going to be microwatts. Since you have a calculator, of course, you can easily plug these values and get the exact answer. But of course, if you don't, you can leave them like this. And this should still be acceptable. But in exam, of course, you have a calculator, you can still go ahead and get the final answer. Now, the next thing that we want to look at, which is the last part of the first question, let's see what they're asking us to find. In the last part, they're now saying, determine the energy absorbed in 3 seconds. Now, notice this, they're now giving us a new range for time in 3 seconds. So how do we get that? Well, we saw earlier to say that power is equals to work done over time. So in this case, since they're giving us the time to work with, and they're asking us the energy absorbed, we can easily we know to say the work done has a direct relationship to the energy that is required. So all we have to do is determine the work that is done during that period of time. And we know to say from here, we can easily integrate both sides. We'll end up with the integral of the power with respect to time. And then in this case, they're saying in 3 seconds. So we're changing from 0 to 3 seconds. So let's see how it goes. The expression for power, remember equation 1? That was an expression for power for this particular circuit. We were given the function of voltage, the function of current. So we ended up with something like this. So let's get this now and substitute it in our expression for the energy absorbed. So we have this is our power. We're integrating this with respect to dt. So this is changing from 0 to 3 seconds. So of course the constants, negative 720, that's just a constant. It will come out of the integral. So we're just dealing with 0 to 3 of e to the power minus 4t with respect to t. So of course, to integrate this, all we have to do is differentiate the power of the argument of the exponent and then divide it here. So we're going to have the derivative of the argument of the exponent is minus 4. So this becomes 1 over minus 4, and then multiplying the exponent itself. So which is e 4t. So this is what we get, the limits being from 0 to 3. From here, we simplify this. The 4 can come out. We have the minus and the minus will give positive. So this is 720 divided by 4. And this is e to the power minus 4t. And this is changing from 0 to 3. Okay, from here, of course, we can simplify this. 720 divided by 4, that is 180. And then we now make the substitution. This is now e. So when we let t be equals to 3, so when t is equals to 3, we're going to have e to the power minus 4 multiplying 3. And when t is equals to 0, so this is now minus e. When t is equals to 0, we have minus 4 multiplying 0. So this is what we get. We simplify this, 180 e to the power, that is just e to the power minus 12 minus, this is now to the power 0, so this is just 1. So this is what we end up with, 180 multiplying this. Of course, the 180, we can send it inside, or we can still leave it here. If you have a calculator, you can still go right ahead and go until when you find the answer. Now, the other thing is, what units will this have? So let's see what we were combining here. So all in all, we had power, and the power was coming with microwatts. So this is what we had. So because this is bringing the micro, so of course this was, we also had a dt here. So from here, obviously we're just getting time. So in the end, this micro is the only thing that is kind of bringing a confusion here. So whatever this is obviously going to give us the correct unit for energy, which is the joules, but the micro will still be here. So this becomes microjoules. So from here, we conclude that the answer that we get here will have the microjoules. So of course, you can still be converting the units and keeping that 10 to the power minus 6 as well. It will still work. Here we're just using shortcuts to predict what the units will be, depending on the things that we're using in the first place. Okay, so this is how you were supposed to work out the first question, and this was supposed to give you all the 10 marks involved here. Now, let's quickly look at the next part. Now, in the next part, we're being asked to make a sketch. Carefully sketch the charge QT stored in the element. Now, if you see what is happening here, notice that now, let's copy this. In this case, current is what we're being given first and foremost. So being given what current is, function of time. But see this, we have expressions. We have 3t, this is in amps. That is if time is ranging from 0 less or equal to t, which is less or equal to 6 seconds. And then we have current is equals to 18 amps if time is between 6 to 10 seconds, and current will now be minus 12 amps. That is if time is ranging from 10 to 15. And lastly, current will be 0 if time is greater or equal to 15 seconds. Now the key thing here is be able to notice that they want you to plot, to sketch a function of charge, not current. So be able to get the difference here. So since they want us to plot the graph of charge here with respect to time, of course, so we need to know how the charge, what charge will be associated to each interval of time. So in other words, first we can start by sketching our graph. Let's create our sketch. So we have something like this. Then we have something like this. So in this case, we've just created our axis. And on our axis, notice that all that we have here is just in the x-axis. Here we're going to have our time, and this is going to be in seconds. And in the y-axis, we're going to have our charge. So our charge, this is going to be, since this is in amps, of course, we're going to get this in coulombs. Okay, with this sorted out, let's start with the first part. So we can actually even define our critical points or our intervals. So you have 0 to, that's 0 to, I can actually, let's move this a little bit. Let's move this so that we can utilize as much of this as possible. So for the first interval, that's from 0 to 6 seconds. So you can put this, we can get this, and you can just put it somewhere. You can even bring it up to somewhere here. So you can say that this is where our 6 seconds is. So this is where the graph will be. Then the next point of interest is going to be, so going up to 15, you can approximate. So the next one is going to be, we can place a 10 somewhere here. Or let's just do it more systematic. Let's say 10 is here, and 15 is somewhere here, 20 is somewhere here, 5 is somewhere here, so that you have a 6 somewhere here. So if this is our 6, this is our 10. The only important parts are the ones which I included here. So I have my 6, I have my 10, the next one is 15. So this is my 6, this is my 10, this is my 15. Then the next one, let's see, 10, 15, and greater than 15. Okay, so for now, let's leave it like this. So let's start. In the first part, let's see how much charge will be associated with this interval. So for that part, we know to say current, a function of time in that interval, is equal to 3t. So let's say for time, for the interval 0 to 6 seconds, for 0 less or equal to t, which is less or equal to 6 seconds, in that case, current will be equal to 3t amps. So current will be equal to 3t in amps. So we know to say current, a function of time, is equals to dq over dt. So this is what current is. So the amount of charge dq will be equal to I t dt. So from here, q will be equal to the integral of I t dt. So in that interval, we'll be using this literally everywhere, but in that interval, to be specific, first, time is changing from 0 to t seconds. Or we can leave out the integral for now. Yeah, let's just look at it. We can still have it, of course. So okay, let's just have it so that we don't forget about it. So that's from 0 to t. We know to say, in that case, the expression for current is 3t. So this is what we are integrating. So if we were to integrate this, so what we're going to have here is, so notice that, okay, so the upper limit, that's from 0 to 3 seconds. So we might as well just put, is it from 0 to 3? That's from 0 to 6. Okay, so from 0 to, we can put a 6 here, but let's keep a t here. What I want to do here first is to just integrate generally. Then we can get exactly what it will be when time is 6 seconds. So in this case, if we just integrate in a general manner from 0 to t seconds, let's say from our starting point, which is 0, to some random time t, notice that our integral of this expression will end up giving us something which is quadratic. So the integral here, of course, this is going to be 3 over 2, because this is a 1. So we'll add 1 to 1, which becomes 2, we'll divide by 2, and this becomes t to the power 2. So this becomes the expression for the charge, a function of time. So if we wanted to use now our limit to say at t seconds, I kept it like this, generally with the t there instead of our upper limit, for one simple reason. I wanted to see how the expression, the function, will be in this region from 0 to, not from here, from 0 to 6 seconds. And of saying it is a quadratic expression. So once we know it is a quadratic expression, the next part is to determine what it will be at the boundaries. When time is 0, so now I'm bringing back the limits. So that's 3 over 2 t squared, and the limit is from 0 to 6. So when t is 6, we have 3 over 2. When t is 6, we have 6 squared. When t is 0, we have 0 squared, which is just 0. So this, note that 6 squared is 36. So you have 3 by 36 divided by 2. So this is what is giving us our charge there. And if we do the math here, so half of this will be 18. Yeah, and then multiply it by 3. This gives us 54 coulombs. So at the boundary, we know to say when time is equals to 6 seconds, then the current, the charge will be 56 coulombs. So in this region, we know to say this is going to end up being not 56, 54 coulombs. So since we know to say that is a quadratic behavior, or that is a quadratic function in this gap, and it starts from 0, we can easily draw something like this, which is quadratic. So in this case, notice that the function ended up spelling it out to us to say this is quadratic. In an event that it would be linear, of course, we would see the function to say this is linear before we make the substitution of what the time is. So this is between 0 and 6 seconds. How about after that? After that, we are seeing that current is just equal to 18 amps. So that is between 6 seconds and 10 seconds. Okay, so for time, so for 6 less or equal to t less or equal to 10 seconds, let's see what they're saying. Well, in that case, they're saying that the current is going to be equal to, that's, let me check that again, that's 18 amps. So current will be equal to 18 amps. Okay, now we saw to say that the charge will literally be equal to the integral of IT multiplying dq. So in this case, again, I'll leave the limits out. I'll leave the limits out. But what you have to get here is that we are building we're starting from some point. We're already starting from time is equals to 6. So charge is more like accumulating here. So when we are evaluating this, you should also remember that there is already some amount of charge which is present, because you're starting from 6 seconds here. So we might as well right here just add up that charge which was already present before we even started. And before we started, we know to say this is now starting from 54 coulombs. So the amount of charge already present is going to be 54 coulombs. So that we are only looking at the new charge which is going to accumulate in the range from 6 to 10 seconds. So from 6 to 10 seconds, notice that this expression now, when we integrate, we substitute what the current is. The current is 18 amps. So we're going to have the integral of 18 dt. So from here, when we integrate this, there's no t there. So we're just going to introduce it there. So we have 18t. So you have 18t here. But don't forget what the limits are. So of course, we're building on that. So on that 54 coulombs, which was already present. But for this expression that we're just adding to this, so this here, the charge is, the time is changing from 6 to the upper limit. The upper limit is 10 seconds. So when we do the math here, so we have our 18 outside. So this is going to be time is equals to 10 minus when time is equals to 6. So this is what we end up with. Then plus the 54, of course, which was already present. So from here, of course, when we multiply, this becomes 180 this side. So this becomes 180, and then minus, then when we multiply with 6, this 108, then plus 54. So of course, these two will just give us minus 58, so that in the end, this, when you get the difference, we get 126 coulombs. Now, notice that this 126 coulombs, it is practically what the charge will be at time is equals to 10 seconds. So if we go to the graph here, at time is equals to 10 seconds, we've got that 126. So let's say our 126 is somewhere here. So let's take this a little bit up. So our 126 is somewhere here. So this is what the charge will be at 10 seconds. But how is the behavior? Notice that in this case, I didn't really reach the part where I pointed out what the behavior will be from 6 to 10. Is it still exponential? Are we still seeing a graph that goes, that is caving, or what? Well, to understand the behavior there, let's look at the equation, the expression just before we substituted, just somewhere here. So in this case, let's get this expression just before we made our substitution. Look at how it looks like. Well, in this case, this is an expression for the charge. So I'm using capital Q, so let me stick to capital Q. This is an expression for charge. And in this case, before we do that, let's keep the upper limit as something general, an expression in terms of time. So if you look at how it becomes here, then notice that we can, when we substitute this will be 18, and then the first one is going to be when t is equals to t, so that is just t, minus when t is equals to 6, so where there's t, I'll put a 6, which is this, then plus 54. From here, this becomes 18t minus, this will be 108 again, then plus 54. From here, notice that this becomes 18t minus 54. So this becomes an expression that gives us the charge. So if you look at this expression, this is a linear equation where if you substitute a value of time here, let's say when time is equals to the one that we've already done, when time is equals to 10, if you plug in a 10 here, it correctly gives you the charge when time is equals to 10 seconds, and the charge is going to be 126, which is what we found earlier. Now, what this equation helps us with is identifying the behavior of the function from time is equals to 6 seconds, from t is equals to 6 to t is equals to 10 seconds. And observing this equation tells us to say this is a linear equation. So this is a linear equation. And being a linear equation, it tells us that in this region, the behavior we see is actually a linear relationship. So if we were to draw the graph here, we're actually going to see a straight line until when we reach our 10 there. So this is a linear relationship. Once this is done, then we can move on into the gap from 10 to 15 seconds. How do we handle that? Well, we go back to the question and we see that from 10 to 15 seconds, again, we are saying this is equal to a constant. So being equal to a constant, we expect another linear relationship, just as we saw when it was equal to a constant 18, it was a linear relationship. So let's see how it will be now. IT is now equal to minus 12. So let's see. So our charge, our current, so our current is now equal to minus 12 amps. So again, charge is equal to the integral of IT, then dt. So of course, this is minus 12. I'll bring it outside. Then the integral of dt. So this is just minus 12. So again, don't forget, it's a build-up. How much charge are we finding here? We are finding that 126, the one from the previous point. So from this point, now how much will be added during this time frame? So this is what we are looking at. So this is going to be minus 12. And then the integral here, of course, is just going to be a t. So we're going to have a t here. And then the starting point is 10 seconds. And then let's keep it general now. We're going to some unknown time, let's say t. And then we are building on the 126 that we found earlier. So 126 coulombs. So how will this become? So this is going to be the 12. When t is equals to t, we're just going to have a t there. And then when t is equals to 10, so where there's t, I'll say minus 10. And then plus what we found, which is 126. So that this is now, or this is negative. This is now minus 12t. And then plus, or multiply this is now 120. And then plus 126. Okay. So from here, of course, we can simplify this a little bit. This is minus 12t. Then 120 plus 126. This becomes plus 246. And then, so this becomes the expression for the charge in that region from 10 seconds to 15 seconds. So again, just as expected, we're seeing a linear relationship. Now, we know it's a linear relationship, but what will be the charge at t is equal to 15 seconds, so that we know the last point in this boundary. So when t is 15 seconds, so when this is 15, we now have minus 12, 15 here, and then you have plus 246. Doing the math here, you see that the charge we end up with is going to be 66 coulombs. So because of that, when we go back to the graph, we know to say this boundary, when t is equals to 15 seconds, the graph, or what you're going to have is going to be a 66, I mean. 66 is just relatively above the 54, so I'll put it somewhere here, and we'll take it up to where the 15 is. The 15 is somewhere here. So the 15 is somewhere here. So now I'm going to draw a straight line. So a straight line starting from t is equals to 10 seconds up to t is equals to 15 seconds, somewhere there. So this is what the graph will look like. Then we have the last part. For the last part, what is the question saying? Now it is equals to 0 for t is greater than 15 seconds. Okay, so now they're saying that, well, if our time, so for time greater than or equal to 15 seconds, they're saying the current is now equal to 0. Well, watch this. We had q a function of time equal to, now equal to 0. Earlier on, not equal to 0. This was equal to the integral of I, a function of time, dt. But we know to say this is just a 0. So if this is a 0, what does this imply? What will be our charge? So if that is equals to 0, what we now have is, well, so it is equal to 0, and apart from that, it's building on what we found, and what we found is 66. So if this is 0, when we multiply it with this, it will still be 0. So here we'll still have a 0, and then plus the 66 that was found. So the charge will remain 66 coulombs, because here there's no more charge which is coming. So because of that, when you go back to our graph, because there's no more accumulation of charge, we have a horizontal line, a constant behavior where nothing is being added. So in this case, we expect the 66 for any time greater than 15 the 66 will be maintained. So we're going to see something that is strictly horizontal like this. So this is generally the graph that we expected to have there. So for all the calculations done here, until when your graph is complete, you get all the marks, and in this case it was 15 marks. Now guys, that brings us to the end of this tutorial. We'll see you guys in the next session. If you want to join any of my live classes, comment in the chat section, then we'll see how best you can join. Now guys, we'll see you next time.